Hello everyone, now we are going to solve the GATE previous year questions. This is the questions of GATE examinations 2019. In the question it is written as a slender uniform rigid bar of mass m. There is a mass of the bar is given which is hinged at O. This is a hinge point you can see in the diagram. Okay. And supported by the two spring with the stiffness 3K and K. A damper with a damping coefficient C is also provided here. For the system to be critical damped, ratio C by under root of Km should be. We have to find out this ratio, and the condition is given that this is critically damped. Critically damped means zeta is equal to 1. That means damping ratio is equal to 1 in case of critical damped. So we all know that C by M, this is the solution I am writing here. C by M is equal to 2 zeta omega n. This is the natural frequency of the system, and this is a damping ratio, damping factor. For the system to be critically damped, zeta would be equal to 1. So it would become C by M, that is equal to 2 omega n. Okay. So what is the value of omega n? This is a system and we have to find out. This is equation number 1. So now we have to calculate the natural frequency of the system. Let us assume that the deflection in the bar is like that. The deflection in the bar is like that, having a small angular displacement theta, because we are going to apply the torque method. So here, when you apply the torque method, in the torque method you just have to provide some small angular displacement to the system, and there will be a theta rotation in this direction. So that means I theta double dot will work in that direction. This is the inertial torque, and for this spring, the torque would be K. This is total length is 3L by 4. This is 3L by 4. So that means K 3L by 4 theta. This is this displacement. Okay, this is the displacement of the spring. So K into displacement multiply torque we are going to consider. So this would be about point O, about the hinge point. So this is 3L by 4. And for that spring, again there will be a force in the directions, in the same directions like that, anti-clockwise. But the spring stiffness is 3K. And what is the displacement? This would be the displacement. This is L by 4 into theta. So this is L by 4 into theta, and torque we are going to consider. So this is about hinged point, that is L by 4. So these are the torque we are going to consider, and you can see here in the diagram all torques are on the same directions, that is anti-clockwise. So we can add them. So finally equations becomes I theta double dot plus K 3L by 4 into theta into 3L by 4 plus 3K L by 4 theta into L by 4 is equal to 0. So we can rearrange these equations. I theta double dot plus this is 9 by 16 KL square theta plus here this is 3 by 16 KL square theta. So again when you rearrange these equations you will get I theta double dot plus 12 upon 16. So that means 3 by 4. Okay, it will cancel out with the 4. So 12 by 16 means 3 by 4. 3 by 4 KL square theta equal to 0. So now the last step, this 3K L square by 4 I theta. So when you compare this with the general equations, you will find that this terms denotes the omega square. So this is omega square is equal to 3K L square upon 4I. So that means omega, this is omega n natural frequency, omega n would becomes under root of 3k L square upon 4I. Okay, what is the moment of inertia? Since moment of inertia we have to calculate because the mass of the bar is given, but if this is the center of mass of the bar, this is the center of mass of the bar, so we know that moment of inertia about point O, that would be Ig plus md square. This is the distance between the center and the hinge point. So Ig is the center and we know that this is ml square upon 12 plus m, what is the distance? D is equal to basically L by 2 minus L by 4. So this would be L by 4. Are you getting my point? This is total L by 2, half of the distance, and this is L by 4, so that would becomes L by 4. So you have to multiply with L by 4 whole square. So when you solve this, you will get ml square, that is 1 by 12 plus 1 by 16. So you will get 7 by 48. 7 by 48 ml square, that is the moment of inertia about hinged point. You just have to put this value in this equation number 2. So from equation number 2 you can get the value of natural frequency omega n, that would be under root of 3k L square, 3k L square upon 4I, and the I value is 7 by 48. 7 by 48 ml square. This would be cancelled out and this would be cancelled out by 12, and you will get here the value 36 k, sorry, L square is cancelled out already, 36k upon 7m. This is what you get. Now we just have to put this value in the equation number 1. This is the equations. Okay, so from equation number 1, what is the equation number 1? C by m is equal to 2 omega n. Okay, 2 omega n means this is the value of omega n, that is under root of, can I write this 36, under root of 36 is equal to 6. Okay, so that would be 6 under root of k upon 7m. So what is the value we have to calculate? We have to calculate C by, in the equations you can C by under root of km. So you can see here C by m is equal to 12 under root of k. So I can write it as under root of 7 multiply under root of m. Yes or no? So this would be cancelled out. So it would become C upon under root of m. Okay, so there will be a replacement of this under root of k in the denominator of this side. So it would becomes under root of km. So you will get here 12 upon under root of 7. So when you solve this, you will get the answer, and that would be 4.53. 4.535. So that is the final answer for this question. Thank you.